Well, I'm going to talk to you about the law of Aboav Weaire in material science. So let's actually begin by showing some movies of this. So this is joint work with Menachem Lazar, currently at UPenn, and Jeremy Mason, and I'm just going to say Istanbul. Okay? Okay. So, see if I can get this to work. So this is mean curvature flow in action. So this is a two-dimensional simulation of what's happening inside metal. Namely, in metal, we've all been taught that inside that the atoms lie in a nice lattice structure. Okay. But that's only locally true. Then you know that it comes a border and then another lattice structure on the other side of the border. So this is what you apply heat to the metal, then the two-dimensional cells, or what we call them, the grains, some of them grow, some of them shrink away, and the nice thing is the law that von Neumann discovered, maybe it's another name more than von Neumann, Mullen, is that the change rate of an area here is proportional to the number of sides minus 6. Yeah, so if you have a hexagon, area-wise is not going to change in size. The other thing I want to point out to you is that this is a simple cell structure. So at every vortex, the three edges meeting, the three grains meeting. And the other thing is that the angles with the meet here is nice 2 pi over 3 or 120 degrees. So the edges are not quite straight. And what I'm interested in is going to be the correlation between if I take one grain and number of sides of all the neighboring grains. Okay. But while we can, let's look at another movie here that Jeremy made. Like this is a foam, and the difference is that here the edges are in fact parts of a circle. We're still having that they meet the 120 degrees at the vertices. It's still a simple cell structure, but you can see how it behaves differently. But still, the property I'm interested in is, given number of sides of the cell, what can you say about the number of sides of the cell of neighboring things here? And you know, I can stare for these movies for hours because it's so fascinating to see this thing. I have the feeling that I'm teaching to the choir because I'm sure that Jeremy Mason, when he was at the Institute, has shown this movie produced here. So I'm not doing anything really new at the moment. And I feel this movie, I remember every night I do the dishes, I had the feeling I watched some similar thing here. Okay?
I remember a seminar that Bob gave to a group of people with combined wealth of one of the chief segregation before you showed this movie.
And they were still also talking about the dishes?
No, he wasn't talking about the dishes.
Okay. So I have two more movies to show here that's just interesting. Here is the hexagonal tiling of hexagons, and you see here that he had removed some edge in the beginning, and you see how this cell has a large number of sides, and it just keeps growing. It slowly keeps eating up everything else. Okay? Yeah, this is the fluid case. I mean, and so you notice that the hexagons are quite stable by themselves. Okay, but if you go in and perturb anything, then the whole thing starts. And you so you notice that the hexagons are quite stable by themselves. Okay, but if you go in and perturb anything, then the whole thing starts. But if you go in and perturb anything, then the whole thing starts. And you so you notice that the hexagons are quite stable by themselves. Okay, but if you go in and perturb anything, then And it does look like the opening sequence of a James Bond movie. Okay? So, also, here, what would happen if you took two metals and you put them next to each other? Well, you could have different sizes of grains in two of the things here. Actually, if you look carefully, this is actually one phenol tiling here to begin with, and here's another small phenol tiling. And it's a little bit counterintuitive. Now, did I start the thing? I forgot how to start the thing. That's bad. No, it's running. And the reason, if you look carefully, what happens is that the action over here is actually faster than the action over here. So this younger metal is going to keep up with the old part. And that's really that the curvature here in these pieces here is bigger than the curvature over here. The pieces here are much more straight. And that's why this moves slower than here. And if you just keep going, you see now that this part here does approach looking like this. It actually goes to a steady state in the long run. So wait a moment. Did someone draw on the white screen here?
Yes. We did.
I was wondering for a moment, but I know there was black and white movie. I was wondering what I was seeing. Okay. Yes, it's forever magic. Eh? But now, the other thing is to actually study this thing in 3 dimensions. So we actually saw one of the movies of Menachem earlier, where, well, it's hard to see the same behavior now in 3 dimensions what happens with this thing. But here Menachem just run one simulation on one grain, how it would look like. And we run it, and you're going to see it moves a lot. It changes, keeps going, and then it shrinks away. I mean, so Randy, I thought you had seen this movie.
I have, but I'm looking at it. Do they monotonically shrink each face? It looks like some of the faces grew, yeah. In 2D, though. The ones that grow. Right? The ones that shrink. But this one without doing any topology change, it looks like there was one that grew. Yeah.
That I'm going to talk about.
Oh, okay.
Yeah, but I was going to do that. So now that was the end of the movies. So now I actually go back to, I'm going to start using Blackboard.
Press power.
Power, and let's see what happens. Ah. So the Aboav Weaire law. So the idea is that we have a grain, and then we're going to look at the neighboring grains. Okay, I can't get all of them into the picture. So the G, E, and N-sided grain and let the neighbors have M1 polyfruit Mn number of sides. Then the average sum is given by 5 plus 6 over n. Which to me is just fascinating that it comes out to be such a nice expression, 5 plus 6 over n. That I find very fascinating. I mean, it's such an easy rational function, so I'm wondering why is this true? Okay? Well, first of all, it's not true. It's not true. I should say is about given by 5 plus 6 over n. It is an approximation, but this is from material science, and they call it a law. So what can I say? Okay? So the truth value is not really there. Okay?
I think Weaire thought he proved. He was just wrong.
Yeah, okay. So I'm going to give 2 proofs of it. One false proof and one true proof of it. Okay? Okay? The other thing I want to point out to you, that we should not call it the Aboav Weaire law, because the initials are all wrong. What we actually should call it is really Law of Aboav Weaire, okay? Because then the initials work. Okay, so let me begin by giving you the false proof.
It should be capital L A.
Yeah, so capital L, A, and W, yeah. So the law, okay? Now it works, okay? That's my only really deep contribution to material science. So, okay, so.
But this is approximately true for both the foam and for the grain.
Yeah. So. Well, I suffer from 3 things here. I'm not a material scientist, so I'm not quite sure what material scientists do. Okay? I also suffer, I'm not a topologist. So for me, I'm not that topological in my thinking. And finally, I'm not an applied mathematician, so I don't really produce graphs in the end to show you how well it matches with reality. Okay?
What do you do?
Well, I mean, I'm a combinatorialist, and for me, I just fell in love with this nice little expression, 5 plus 6 over n. It was such a nice little expression that I really wanted to understand it. Okay? So define curvature of a 2-cell F to be capital F to be 6 minus number of sides of the 2-cell. And then for a simple subdivision of a 2-manifold M, we have that if I sum over all 2 cells of the thing, kappa, the curvature of each face, you get 6 times the Euler characteristic of the manifold. This is not hard. You just prove it using the Euler characteristic is just F0 minus F1 plus F2, plus that I'm having here a simple subdivision, so you know that 3 times the number of vertices is 2 times F1, and this comes in. Okay? So it's not hard. Well, notice that for a torus, we do have that the Euler characteristic is 0. And it really is that the torus is flat. that there's no curvature when you look at the torus. So hence, so here's the probably Weir's law. Assume that G together with its neighbors is locally flat. I mean, it's an unreasonable assumption, but let's do it, see what happens. What does it tell us? Tell us that if you sum all this curvature, 6 minus n plus sum I equal to 1 to n 6 minus mi, this should be equal to 0. Well, do the algebra now. You notice here there's n terms of n, so I get 6n here. Then we'll move the 6n in front, minus n here, so 5n minus 6. And this is equal to sum I equal 1 to n mi. So now, wait a minute, plus 6. So now I take divide by n on both sides. You see, in fact, we get here that 5 plus 6 over n is, in fact, the average. So there's the first false proof of the law. So let's go on and actually give a correct proof of this thing. Well, to give a correct proof of it, you should think about an analog like Taylor's formula. We do Taylor expansions, but Taylor expansions might not be true. But the Taylor expansion, if you cut it off and you find the right error term, that's actually going to be a true expression. Okay? So Taylor's formula with error term is actually indeed correct. So the problem is, what is the right error term here? So I have a proof. Well, we can apply Gauss-Bonnet theorem to something lying in the plane. So let me draw the picture. If this is my region D, Gauss-Bonnet says that if you integrate over the boundary, over the curvature, plus you have to also to look at the angles happening at the boundary here. So when you go around this thing in opposite orientation, you have to measure these angles. No, I didn't. So alpha 1, alpha 2, alpha 3, so on. This is 2 pi times the Euler heuristic of the region D. So this Gauss-Bonnet in the plane. Well, now when I apply this to a grain, well, the thing to remember about the grain is that all these angles here are 2 pi with 3, that all nicely in this application, they all come together in nice 120 degrees. So all the alpha i's here are pi with 3. So a grain G with n sides, what do we get? We get integration over G over the curvature plus we get n of these, n times pi with 3. And the Euler heuristic of the grain is 1, so we get that thing. So if I simplify I move this to the other side. I divide by pi with 3. You get 6 minus 3 over pi times the bond over the grain of the curvature. Now, so now I'll apply this thing to the grain and all its neighbors. We get n plus some I equal to 1 to n mi. Well, we get 6 minus 3 over pi, the boundary of the grain G, kappa dl, plus 6n minus 3 over pi, some I equal to 1 to n, boundary of delta gi, kappa dl. Well, now, the nice thing here is that all these curvatures will be integrating in this picture. When we ground G here with the curvature here, it cancels with the curvature going the other direction here. Namely, so let R be the union of all the grain and all its thing. What do we get? We get n plus some I equal to 1 to n mi is equal to 6 minus plus 6 over n minus 3 over pi boundary of the R kappa dl. Well, move the n across here. You get 5 over n, and finally divide by n. And we get 5 plus 6 over n here. And here is the law of Aboav Weaire with the nice correct error term here. So it's nice and true. Of course, for the working material scientist, it might not be very practical to integrate over the boundary here. So you still might want to look at, somehow want to say that, okay, this is very nice, but we might want to look at what happens in some sort of approximation to this formula to try to understand it. Oh, no, I forgot I missed divide by n, so thank you very much. So after 2 dimensions, we had to look at 3 dimensions. What happens? Well, so the thing well, again, it's a simple subdivision. So 3 cells meet at every edge. And the dihedral angles where they meet is 2 pi over 3. And then 4 edges meet at every vertex. And the angles comes out here to be cosine of, r cosine of negative a third. So what is this? So that's like 108 degrees, something like that. Okay? But you're going to see that this constant appears again. And yet again, to prove the right result here in 3 dimensions, yet again we're going to have to use Gauss-Bonnet. Which to me is a little bit unfortunately, because Gauss-Bonnet applies to a nice two-dimensional manifold. So I used Gauss-Bonnet. I'm going to use it in the two-dimensional case. I'm going to now use it in the three-dimensional case. But somehow you feel something's lacking, because what's going to happen if you want to prove something similar result up in 4 dimensions? There is no Gauss-Bonnet to apply it up there. So I feel that there is something wrong in the approach in here, because it stops at 3 dimensions. It doesn't go on. Right? So D polyhedron with piecewise boundary, and then Gauss-Bonnet states that we have integral of the area of the boundary of D, and we do a two-dimensional integral, plus the boundary of D of the one-dimensional things. And I love all these long expressions of beta. Kappa times E2 times V of the length, plus the angle deficiency is equal to 2 pi times the Euler heuristic of the boundary. So this kappa there, that's the Gaussian curvature. This is curvature along the edges, and E2 here is like the second Fourier vector. And alpha here is the angular defect. So the angular defect, let me just remind you about one of the precursors of Gauss-Bonnet, and that's really Descartes' theorem for polyhedra. Namely, if you take for every vertex of a polyhedra and you measure the angles coming in there and you sum them up, and then you take 2 pi minus that, the whole minus the whole thing comes in, that's the angular defect. And if you sum over all the angular defects of polyhedra, you get 4 pi. And in fact, this result was actually a precursor to Euler's formula. Euler's formula was originally proved using this result. So it's not surprising here that we have, for the number of vertices here, that this actually comes in Gauss-Bonnet. What? I don't know, but this is, you have to look it up in Spivak, I think. Okay. Okay. So now, we can state the three-dimensional law. And I'm going to need the following quantity, 2 pi minus 3 pi r cosine minus a third, i.e. that is the angular defect along one of these grains at the vertices. And that's why that comes in. So I'm just going to state what comes out. And really, 1 over n, some I equal 1 to n. So the average number of sides of for an n-sided grain, and then the average number of sides of all the neighbors, is 2 pi over a1 plus 1 plus 1 over n 2 pi over a1 plus 2 minus, and now comes the whole error term in, but it's really what we have to use copy from here. 1 over n, 1 over 2 over a1, sum j equals 0 to n. First we have for each grain di, we have the Gaussian curvature. And then for each, we have to look at integrating this to curvature along the edges also. Kappa E2 times V ds. So really, the proof, we just apply Gauss-Bonnier to G, what I call G0 to get the sum to work, and G1 through Gn, all the neighboring grains. And if you take all of that and you add it all up and you transfer the thing, this is actually what comes out from it. And it's not that very nice, because oh no, I broke the thing.
You can put it in your pocket.
Yeah, thank you.
That side.
Okay, don't forget at dinner to actually hand it back. Okay? So in the two-dimensional case, when we add up the curvatures, then it nicely cancelled in everything between here. However, when you summing up the curvatures here, both the two-dimensional curvature and the one-dimensional curvature, it doesn't cancel out. So the error term here might be actually worse than in the two-dimensional case. In fact, let me just also write it down numerically what it's going to be. So numerically,
So you're thinking of that last curve as an error curve that you want to be small.
yeah, I want this to be small. And in the data Jeremy and Menachem ran on it, it actually comes out to be small, but it's not too bad. Okay? $12.397 plus 13.397 over n. Okay? And the nice thing to compare with here is that the two constants appear to differ by 1, and it's just like in the original law, it's 5 and 6 here, and here you add 1 to 12, you get 13 here. So it's nice fitting. Okay? So there's the three-dimensional law. However, all the laws I presented to you, the two laws I presented to you now, are sometimes as local laws. I.e., there really is a look at the grain, and it could be any grain inside this thing. Well, for the material scientists looking at this issue, they do not doesn't look at a particular grain. They're more interested in looking at all of the grains. So what they're going to define. No, suggestions of things up in 3 dimensions, but it wasn't this explicit, and was also for very strange subdivisions of space. So it didn't apply to the mean curvature growth, for instance, of that they're interested in. Yeah, yeah. I think it was that he had things that were just like prisms, but
Yeah,
yeah.
yeah.
Okay. We're
Call them lenses, right? Infectional lens.
yeah. So global relations, namely, let Gn be the average over all n-sided grains G of the average of number of sides of the neighbors of G. Namely, you take the whole subdivision of the plane, and then you look, say, for all 5-sided grains, and for each of them, you compute what the value would be of the law, like the average, and then you take the average of all of them, or rather, for mathematical performance, you take the expected value of all these averages. And then Weaire suggested that the correct law should be the Gn is about equal to 5 plus 6 plus mu2 over n, where mu2 is the variance of the number of sides of the grain. For instance, you can see that if I take the hexagons in the plane, here every grain is a hexagon, so there's no variance. So in here, in this case, mu2, the variance is 0. But the only thing you can plug in this law here is in fact n equal to 6, agree? So I get 5 plus 6 over 6, which in fact is 6, because all the adjacent things are 6 here. Okay?
So he suggests this is true, not for an evolved grain state, but for any self-recovery, any infinite self-recovery.
And yeah, okay, but you have to have these 2 pi with 3 angles and so on. Yeah. And let me show you the idea where this actually comes from. So let's do the ansatz that G of n is 5 plus some constant over n. They just said, hope it's going to be this way, that it's going to be a nice hyperbolic relation. So then ngn is going to be 5n plus a. Now, take expected value, i.e. we can look at ngn Well, the expected side is here. We get 5 expected value of n, and the constant goes out. But now it's easy to see the expected value of number of sides of the grain is going to be 6. So this term is going to be 5 times 6 plus a. And now by double counting, this expected value turns out to be the expected value of number of sides squared of the grain. This is easy to see by just you write down what this expected value is. Namely, you have this is just n times the average, the expected value of the average, but there's no average anymore because you're not divided by n. So use the sum of number of sides of the neighboring thing. And then by switch the order of summation, you can get this result. Well, this thing is the expected value of a random variable squared. That's just the variance plus the expected value squared, which is then mu2 plus 6 squared. So if you now solve this thing, we get a is equal to 30 cancels with 36 there, you get 6 left. A equal to 6 plus mu2. So that explains now why this constant a is 6 plus mu2. So in fact, this.
So this is a proof, for example, that if you have any celtic coupling of the torus, then that theorem is true under those.
Yeah. So you can actually, I mean, when I was trying to truly understand this thing, I tested it with the Archimedean Celtic compositions. You can tile the plane with squares and octagons, and it works out here. I mean, it's a little bit big in the M5 case, but on average actually works out very nicely. So now, this was so far we got in our paper. And I was thinking there must be something more to do here. So I was looking at that if I took 2 grains, G and H, so this is an M-sided grain and this is an N-sided grain. I decided, let's look at the number and joint neighbors of these things. I'm going to look at all the whole neighborhood looking of all these grains. So I want you to note that number of neighbors is m plus n minus 4. Namely, you have m neighbors here. What is m minus 3 of them that doesn't touch goes to h. There is n minus 3 of them on the other side here. And then we had to count the ones above them touch over here. That adds up to m plus n minus 4. And then, whereas before you were taking these averages over all grains, now I have to be careful because in order to get a pair of grains, I should really have to select an edge and look at its neighbors, which means I'm looking at different probability distribution. So the many distribution, now I'm picking a random edge. And actually, to do this, I actually take an edge E here with an orientation. So I have one grain to the left and one grain to the right. And then I can now look at the same quantity and namely GMN, namely what's the average number of number grains over here. And what I actually get out is this is about equal to 5 plus, well, I get here downstairs m plus n minus 4, which is the number of grains. And upstairs, I get a nice big mess. Namely, what happened was I was working this problem. I was coming up with formulas saying it must be like this. I sent an email to Jeremy Mason, and he said, no, that's wrong. Doesn't work. And then I was working it through again and come up with an improvement. And he said, no, that's also wrong. And when I finally got to this thing, he wasn't complaining anymore. Okay. Also, the nice thing here. Yeah, he compared with real data. Okay. So he's actually an applied mathematician. He looks at real data, where I look at really nice things I can understand like this. Okay. And check it against Archimedean tilings, which actually is something. It's a little bit of a fake way to do it. Okay. So we got law like this. So I have to tell you what it is. Mu2 is still the variance, and mu11 here is a covariance upon on two neighboring grains on their sides. So yet again, you notice that you have this nice hyperbolic relationship between this thing. But it's not as good because when you go and look at Weir's suggestion here, the nice thing is that the covariance between two neighboring grains doesn't show up here. So it actually does say something that a large grain would have neighbors that are small, and a small grain will have neighbors that are large. Agree? There's an inverse correlation to here, and in order to press this loss furthermore here, I would force to use the covariance here, which somehow it's a beautiful thing here that this doesn't have the covariance in it. The other thing to look at also is what would happen if I do the situation where I have 3 grains, m, n, k number of sides, and then you have to look at all the joint neighbors of that. And yet again here, the expected value of the average, 5 plus, well, this time around, the number of neighbors comes out to m plus n plus k minus 9. 3 of the covariance plus mu2 squared over 12 plus 2 times the variance plus 9. So my goal has just been trying to understand more how did this behave. Namely, because if you look in the thing, there's so much noise in the system. So I'm wondering that if you have one grain, how much can you say further away? And you can't say very much further away because the noise in the system comes in. So that's why I'm trying to press and see how far I can actually press this law of Weaire here. How far can I press it? And the question is, I don't know how useful this is because both of these laws here has the covariance coming in, and that seems like already knowing that it's bad correlation with what the correlation is to say it here. So I don't know quite what it is, how useful this is. And finally, I try to press it one more step further. Namely, if I have a grain, well, then I have its neighbors. But then, along the center grain, along an edge sticking up from the center grain, there's going to be a unique grain coming over here, and I will call that a second neighbor. So I've been looking at what can you say in this case of the average of second neighbors, and what I get is the covariance. So E is the covariance of the second neighbors minus, here's the interesting term, 6 squared times mu E over mu 2 times N. Well, the covariance, I believe this being positive on between two things here. So this actually shows the covariance, that the relationship actually goes the other way, the sign changes here. So that would be the average of the second neighbors of the grain G. But I had to start emailing Jeremy Mason again, make him test things and see how it's working. So thank you very much.